48. The calcium ions in human blood serum are necessary for coagulation. And I will spare you the picture, which is in figure 15.5. We don't need it to answer this question. Potassium oxalate, which is K2C2O4, is used as an anticoagulant when a blood sample is drawn for laboratory tests because it removes the calcium as a precipitate of CaC2O4H2O. It is necessary to remove all but 1.0% of the calcium 2+ in serum in order to prevent coagulation. If normal blood serum with the buffered pH of 7.40 contains 9.5 milligrams of the calcium 2+ per 100 mils of serum, what mass of K2C2O4 is required to prevent the coagulation of a 10 milliliter blood sample that is 55% serum by volume? And then they give us this little hint here. They say all volumes are accurate to 2 significant figures. Thank you. Note that the volume of the serum in a 10 milliliter blood sample is 5.5 mils. And then assume that the KSP value for the CaC2O4 in serum is the same as in water. Okay, so I went to the back of the textbook to find out what that KSP value is that we're probably going to have to use somewhere along the way. And KSP for that calcium oxalate CaC2O4 is 1.96 times 10 to the negative 8. But now, where do we start? I have no idea. No, I'm just kidding. Let's see. We want to find out what the mass of the K2C2O4 is, right? That's the question. That's always going to be in the back of our head. But we have to use this KSP value. Now remember, the KSP value comes from the 2 ions, the calcium and the oxalate, right? CaC2O4. Now, what information do we actually know about? Do we know about calcium values or do we know about the oxalate values? Well, let's see. They tell me, okay, 1% of calcium, so that's information for calcium, 9.5 milligrams of calcium, so that's more information about calcium. They give me 10 mil blood sample, 55% serum, but I don't see any values that have to do with the oxalate for right now. So the first thing that I'm going to do is, since I have information about the calcium, I'm going to try to mold it into what I need. Now, remember, if we're finding out for solubility or precipitations, right, we're talking about precipitates, maybe we should just write out the equation for the calcium oxalate and just put it in the back, on the back burner. So we have calcium oxalate, CaC2O4. That's the solid. This dissociates into its 2 ions. They told us that it was Ca2+, so thank you for that, Ca2+. That is aqueous, there's a charge. And then, since there's 1 calcium for 1 oxalate, the charge for C2O4 is a 2-. Plus 2 minus 2, that equals out. So that's aqueous. Okie dokie. So I'm just going to throw this over. I guess I could throw this. Oh boy. Let's see. We'll put this a little bit more over here. Let's throw this in the middle because we'll kind of be looking at it. And then we'll throw this a little bit off to the side. Okay, beautiful. There we go. Okay. So now let's work with what we have. Remember, if we want to use KSP values and we want to put a value for the calcium, this has to be in molarity, right? So I need a molarity value. So molarity of the calcium equals question mark. They gave me 9.5 milligrams of calcium. So I need to somehow turn milligrams into molarity. So let's see. They told me that I had 9.5 milligrams of Ca2+, and that's per 100 mils of the serum. So per, remember, means division, and this is 100 mils of serum. Blood serum, basically, right? Now remember, if we want to solve for a molarity, and maybe I'll put that up here, molarity equals moles of the solute, which is going to be the calcium. That's the thing that's in the whole solution. So it's moles of the calcium divided by the liters of solution. And the liters of the solution is the whole blood sample, right? Not just the serum. Because you notice how they say the volume of the serum in 10 mils of blood is only 5.5 mils. The solution is the whole entire serum, solvent and solute. So in this case, we're looking for that specific blood sample, not just the serum. So somehow I have to get rid of the serum value because I want liters of blood. So we're just going to do some conversions. It doesn't matter what you work on, right? But the idea here is that I want to go from milligrams of calcium to moles of calcium, right? Divided by liters of the blood. Okay. So that's the object here. I have to change the numerator and the denominator. So let's just write it out one more time. And then let's get to it. Okay. So maybe the first thing I'll do is I'll say that let's get rid of this milliliters of serum. Now, they did tell us that we did have 5.5 mils in the whole entire 10 milliliter blood sample. So I can, use that information. So I'm going to times by the ratio. I don't want my mils of serum anymore. That goes on the top. Remember, whatever you don't want always has to go on the opposite side. So mils of serum, that goes on the top. And the liters, actually they said milliliters. So 10, well, I don't want to put the number yet, but mils of blood goes on the bottom. In the 10 milliliter blood sample, so that has to be 10, there are 5.5 milliliters. So 5.5 goes on the top. For every 5.5 milliliters of serum, there are 10 milliliters of blood. And now the milliliters of serum cancel. We're almost there. We're at milliliters of blood. Now we just have to go to liters. Because remember, molarity is moles divided by liters. But that's easy. Times by the ratio again. We could just say mils to liters. And maybe I'll just put the word blood in here just to show you that we do have the solution. But it's the standard mils to liter conversion. 1,000 mils equals 1 liter. And goodbye to that. So now we have our denominator. Perfect. Now we just have to get those milligrams. So let's keep going. Times by the ratio. Maybe I'll put that in. There we go. We don't want milligrams anymore. So milligrams goes on the bottom. It goes on the opposite side. Let's go to grams first, because from grams I could get my moles, right? So milligram to gram, that's 1,000 to 1. Milligrams will cancel. Now I'm just left with grams. And now we can get to moles by doing just a mole to gram conversion, right? Grams of Ca2 plus, moles of Ca2 plus up on the top. We got, for every 1 mole, it is what it is on the periodic table, which is 40.0 40.08. Okay, so let's do this math, right? Grams cancel out with grams, and we're left with moles. All right, so we're going to get the molarity of what that calcium is. So let's see, I'm just going to start canceling out numbers here. Let's see, 1,000 with 1,000, that could get canceled out. Everything else, let's do the math. So 9.5 divided by 100 times 5.5 divided by 10. And then it seems like I have to divide by 40.08. I get 1.3036. This is not the final answer, so I'm not rounding it to 2 sig figs. And this is times 10 to the negative third molarity of the Ca2+. Okay. So, first stage done. We found out the total molarity. So, from the 9.5 milligrams that we started with before, the total molarity for that calcium is 1.3036 times 10 to the negative third molarity. Next part. Now remember, it says that we want to remove all but 1% of that calcium. So this is the total molarity. When we remove the 1%, that means that 99% of this is going into a precipitate, right? Or a solid. So we want to find out of 100%, what is only 1% left? That's the molarity that we want. We want the 1% because it says right here, we need to remove all but 1%. 1% of the Ca2+ is remaining. So let's just do a easy formula, right? Percent is always part over whole times 100. The entire 100% sample is 1.3036 times 10 to the negative third. And this would be X on the top, right? Okay, so let's see. We can divide by 100 on both sides. Okay, so 1 divided by 100 is just 0.01. And maybe I'll move this up a little bit. Oh, what's going on here? There we go. So I get 0.01 equals X over 1.3036 times 10 to the negative third. So I'll just times that. 1.3036 times 10 to the negative third times 0.01. And now here's my 1% remaining. My 1% remaining is 1.3036 times 10 to the negative fifth molarity. That's what's remaining in the solution. So I'm just going to be putting that all over here just to show you guys. So I'm just going to highlight this. So this is the 1% that's remaining. Maybe what I'll do is definitely we should keep the total. For some reason or another, maybe we need to use that total value, but all the other conversions we don't need. So pause the video. But this conversion down here, we're done with this. We don't have to see this ever again. We don't have to see this. So I'm just going to get rid of that. We already used our molarity formula, so I can get rid of that. And basically, I'm going to get rid of everything except for that total value, just to show you that, you know, the 1% is from this total amount. So maybe I'll just put that over here. Okay, so now from here, we can say that we have the concentration of the calcium, right? And from here, we're going to find out how much oxalate is required for this remaining 1%. So I don't know what this oxalate is, the C2O4, so I'm just going to label that as X. Now I'm going to use my KSP with the equation, right? The general equation for KSP is this right here. So let's just write out our specific one for this case. We have KSP equals the concentration of the Ca2+ times the C2O4 2 minus. No need to raise any to the coefficients because it's a 1-to-1 ratio. And the KSP was what we found out before from the back of the book, 1.96 times 10 to the negative eighth. The calcium, the 1%, is 1.3036 times 10 to the negative fifth. And we're solving for that oxalate, which is X. So 1.96 times 10 to the negative eighth equals 1.3036 times 10 to the negative fifth times X. And now we're just going to divide by 1.3036 times 10 to the negative fifth times 10 to the negative fifth. Okay, cool. And now let's see what we get here. 1.96 times 10 to the negative eighth divided by this answer. And I get 1.504 times 10 to the negative third molarity. And I just want to make sure I got that right. 1.504 times 10 to the negative third molarity. And that equals X. And remember, that was the X value here. So I have 1.504 times 10 to the negative third molarity of the oxalate ion that is needed to basically start precipitation from that calcium. But now, they're asking for what is the mass of the K2C2O4 that's required to prevent coagulation if it's 55% volume. Okay, so now we need to account for all of the molarity that was used for the C2O4. So pause the video if you need to write down this amount, but basically we're done with this calculation, but there's a few other things we have to do in order to get the final answer. So this is going bye-bye. And now we have to take into account the total mass, right? Remember, this is the molarity for just the 1%. Now, remember when we went back to this total? I'm so glad that I kept this value because we have to also take back the 99% amount for the C2O4. Remember, for every 1 calcium, 1 oxalate is going to come with it. So we basically just have to find out what 99% of this 100 total, because that's going to be added up with this molarity here. So if we just do quickly another percentage equation, 99% equals something divided by something times 100. The total, remember, is that's still the same number, 1.3036 times 10 to the negative third. And we'll just solve for X, right? Divide by 100 on both sides. Divide by 100 on both sides. I get 0.99 equals X. Ooh, what happened there? X over 1.3036 times 10 to the negative third. We could cross multiply it out to get that 99% molarity. So 0.99 times 1.3036 times 10 to the negative third. I get 1.29. That's good enough, right? 1.29, I guess if we round 1.291 times 10 to the negative third molarity. Now that's of the calcium, but remember, for every 1 calcium comes 1 oxalate. So this would also be the molarity that is required of the oxalate to clear the calcium. So I'm just going to add this molarity up here, 1.291 times 10 to the negative third molarity, C2O4, 2 minus. Because the combination of the two is going to give you the 100%. Okay, but remember, molarity is not additive, only moles. So we just have to convert these molarities back into moles. So just pause the video if you need to. I'm just going to get rid of this. So bye-bye. And now I'm just going to actually, I could just do it over here. Remember, going back to the molarity formula, molarity equals moles divided by liters, right? So if I want to solve for the moles, just cross multiply molarity times liters, right? So moles equals molarity times liters. So let's find out for the first one. Moles equals the 1.504 times 10 to the negative third molarity. And that's being times by, remember, the total volume was 10 mil, right? The blood sample is the solution. So the liters is the 10 mils, but that's the same as 0.01 liters. So I'm going to times that by 0.01, right? Okay. So let's get that number. 1.504 times 10 to the negative third times 0.01. I get 1.504 times 10 to the negative fifth moles. And now let's do the same for the next one, right? Moles equals 1.291 times 10 to the negative third, also times 0.01. So 1.291 times 10 to the negative third times 0.01. I get 1.291 times 10 to the negative fifth moles. This should be moles. And this is of C2O4, 2 minus, and this is C2O4, 2 minus. So now what would be the total number of moles? Oh yeah, we just add them up. We're getting there. So let's see. This value plus this value in the calculator, I get 2.795 times 10 to the negative fifth moles of C2O4, 2 minus. Okay, now almost there. Let's just use our ratio. Remember, we still want to find out the mass of K2C2O4. So if I write down K2C2O4, right? And in one whole K2C2O4, I have one oxalate. I have one KC2O4, right? So for every one K2C2O4, I just have one C2O4. So it's a 1-to-1 ratio. So this would also be equal to the same amount of moles as the whole compound. So this would be 2.795 times 10 to the negative fifth moles of K2C2O4. And from that information, we could finally find out a mass. Oh my goodness. So maybe I can just, let's see. Maybe I can take this and bring this up a little bit, because all we have to do now is just do a mole to mole ratio, right? Or mole to gram ratio. But we could do the quick version, right? 2.795 times 10 to the negative fifth moles of K2C2O4. Remember, if we just want to go to grams, right? If we're going to grams of K2C2O4, all we have to do is just times by the molar mass. So I'm just going to go on the periodic table and find out what the molar mass is of K2C2O4. So let's see. Potassium is 39.1, so 39.1 times 2, plus 12.01 times 2, plus 16 times 4. So I get 166.22. So I'm just going to take this amount of moles and times it by 166.22. 2.795 times 10 to the negative fifth. And now, since they did say, with the 2 sig figs, I guess we should have 2 sig figs at the end. So 4.6. 4.6. And maybe I'll move this. 4.6 times 10 to the negative third. And that's grams. Yep. That's grams of the potassium oxalate. And that is your final answer. Oh my goodness, this one was crazy. And just for one last thing, for anyone who is asking, but wait a minute, we didn't use this pH value. That was extra information. Didn't need it. They just said that normal blood serum was pH of 7.4. A little bit basic. But we didn't need it in this whole equation. Just make sure. Sometimes they'll throw out some additional information, but don't get scared. All right? We got this one. So hopefully this helped. Let me know what you think. Subscribe to the channel if you want to help us out. Thank you so much for that. And I will see you in later lessons. Okay, bye-bye.